transmitted something with priority 112 or identifier 112, and the bus accepted it. So the point of that in the test case is to make the bus busy. That means that other messages must be queued. Now we transmit something with ID 113, the bus is busy, and with 114, the bus is busy. Now we call the protocol layer from below, and we say the bus is confirming that it sent message with ID 112. So what should happen? Well, this protocol layer should now send the next queued message, and which one should it be? 113, and which one was it? 114. So we can see that the code sent the wrong message. It didn't give priority to the correct message. And the test case that demonstrates that is nice and short, and it's easy to see what the problem is. What was the problem in the code? Well, no matter what form of ID you had, it was stored in the code in an unsigned 32-bit integer. But because it's necessary to remember whether your ID is extended or not, the top bit was used to record, to differentiate an extended from a standard ID. So when you compare those IDs, you must remember to mask off the top bit. And they have forgotten to do that. So that's an example of the kind of error in this, it's all C code, that we can find by generating quite short tests. Okay, so how's this going? Well, we're having to write a quick check specification, which is almost an implementation of AutoSAR in Erlang. So we have a lot of code to write. How is it working? Here's some figures. This graph shows the size of the implementation in C code and the size of our corresponding specifications. So as you can see, we've written quite a lot of formal specifications. We've written, 16,000 lines? But we're testing 60 to 70,000 lines. So that's quite a good ratio. But normally you need more test code than that per line of implementation code. Here's another comparison. We were actually able to get hold of a test suite for one of the components, a FlexRay interface, so-called. And we could compare the size of our test code to the conventional test code. Now, unfortunately, this stuff has to be configured, and that means XML, lots of it. XML is big. We're able to get away with about half as much XML as the developers of the standard test suite, but there's still a lot of it. However, don't worry about that. Look at the size of the code. The quick check test code is 16 times smaller than the test suite that otherwise had to be written to test this stuff. So that corresponds into lower cost for testing the software. Lower cost at the same time as we're getting better testing. Okay. How do we know that our specifications are right? We're writing, I said, 15,000, 16,000 lines of code. Of course, it's full of mistakes when we first write it. So when a test fails, what that tells us is there's a bug either in the vendor code or in our specification. And bugs in the specifications are very common. So we need to decide which is it. So you can see that quick check tests the vendor code, but at the same time, the vendor code tests our models. And without that testing, then it would be very hard to get our models right. So we have to decide what is correct, and of course, we can read the standard. Sometimes that works. But what if you can't tell from the standard what the behavior is supposed to be? Or what if we think it means one thing, and the vendor thinks it means something else? You have to have an oracle. Ours is Volvo. Thank goodness for that. So sometimes we just ask Volvo to lay down the law and tell us what do they want. So far, these are figures from about March, actually. We've been testing code from 6 different suppliers. We found more than 100 issues in March in the code, and more than 30 of those were actually bugs in the standard itself. The standard is an evolving document. Don't think because it's called a standard that it's bound to be correct. It certainly is not. And it looks as though we're on target. So later on this year, then the code that's really going to go into Volvos will be certified by property-based testing. Buy a Volvo for your next car. It'll work. Okay, so I wasn't quite sure how long this would take. I have a couple of other stories I would like to tell you, but I'm going to skip over this one. It's a good story. Oh, such a shame, but the one that follows is even better. This is about how we helped to fix an eventual consistency problem in a NoSQL database. Oh. So, since you've seen which database I'm talking about, I just want to make a point here that sometimes I give this talk. It's a nice talk in its own right about how we tested this, distributed, large-scale database. It's a key value store. And sometimes I give this talk about how we found and fixed an eventual consistency problem. And then somebody in the audience says to me afterwards, oh, I was thinking of using React, but now I know it's so buggy, perhaps I won't. And I mean, that is really head in the sand stuff. I'm sure that the other competing databases are at least as buggy, but we have found a lot of work has been put into testing React with property-based tests very thoroughly, and it's really a great product, great high-quality database. I want to tell you another story that I'm very, very fond of, and it starts with a message to the Erlang mailing list about 5 years ago. I'll read it to you. We know there's a lurking bug somewhere in the debts code. We've got bad object and premature end of file every other month the last year. We haven't been able to track the file down because the file is repaired automatically next time it's opened. This was sent by a guy called Tobbe Törnqvist at Klarna in Sweden. So, I'm sure we all feel Tobbe's pain. But what's he talking about? I know the context of this. You don't. Let me test it for you. First of all, Klarna. Klarna is a Swedish company that provides invoicing services for web shops. It's much more exciting than it sounds. They have built, so they have grown in 5 years to more than 600 people. So it's a really, really good business idea, and they're growing like crazy. They've also built their system entirely in Erlang, so they're now one of the biggest Erlang users. They store all their data in a database called Manesia. It's a distributed database. It gives you transactions, distribution, replication, and so on, and it has a funny name. The developers at Ericsson wanted to call it Amnesia, but their managers wouldn't let them. Amnesia. So Manesia itself stores its data using a back end. And the back end for disk storage is called debts. It provides tuple store in a file. And that in turn uses the file system. So debts, that's the component that Tobbe was talking about in his mail. That's the one that doesn't work. And I thought, well, if it's failing every month or two, that sounds as though it could be a race condition. And I was interested in testing for race conditions at the time. So I thought, well, let's take a look at it. So now I want to explain how we test for race conditions using QuickCheck. And to do that, I'm going to go from the sublime to the ridiculous. Imagine that I want to test this thing. Does everybody recognize my drawing? You have them in supermarkets in Sweden, at least older supermarkets. I guess they're in supermarkets here too, at the delicatessen counter. So you can take a ticket, and then when it's your turn, you get served. So if I were to model this in Erlang, I'd need to write a couple of functions, maybe a take-ticket function and a reset function. Every now and then, a guy comes along and replaces the roll of tape. So let's imagine that I want to test these two functions. Here's an example of a test that I could write in Erlang. Look at it. It's exactly the same kind of test that I showed you for the base64 encoding. It's the usual form. You call the functions in some sequence, you figure out what the expected result is, and you check. That's a pattern match. You check that the result really is what you expect. But wait a minute. The whole point of a ticket dispenser is to regulate the flow of a concurrent set of customers to one delicatessen counter. So what is the point of running a purely sequential test? This is not the behavior I'm looking for. What I want to do is to run some parallel tests, like this one perhaps. So this represents, first of all, resetting the dispenser, and then maybe one customer takes 2 tickets, and another customer takes the third. So what results might I see here? Well, the reset will always return OK. First customer could get tickets 1 and 2, and the second one ticket 3. Or the first customer might get tickets 1 and 3, and the second customer might leap in there and get ticket number 2. But I better not see this. I better not see both customers getting ticket number 1. Because if I do, something has gone wrong. So, how many correct outcomes are there for this test? Well, there's 3 different ones, right? Depending on which ticket the second customer gets. And remember that the way that developers know to write test suites is to compare against expected values. What are the expected values? Of course, you could calculate 3 different expected values, collect the results, and check that you're seeing one of them. But this is a tiny test. I really want to run tests like this. How many possible outcomes are there of this test? Luckily, I figured it out for you. 42, of course. So, nobody in their right minds is going to try and figure out all 42 possible correct answers and then enumerate them in their test case. And if somebody did try, they'd get it wrong. So what this shows is that testing parallel behavior, it's fundamentally impossible with the techniques that today's developers use. The only way that we can reasonably make a parallel test, is to recognize a correct outcome using some kind of property. It's a killer app for property-based testing. Okay, so the way that we test it is we model the dispenser in the same kind of way that I modeled the C code. We generate, for sequential tests, sequences of calls. We model a state. In this case, a single integer is enough. And we check post conditions that say that the result we get corresponds to the state before the operation. So I can make a sequential model very, very easily. How can I decide, though, whether a parallel test case has succeeded or not? Here's the same test case drawn on its side this time. So this represents a successful test. But how can I tell? Well, because there is some order in which I could interleave the parallel parts that explains the actual results that I see. So if I find that order and just make a sequence of the results, then the sequence of results I see should correspond to the model. My post conditions should be satisfied. So what we do to run parallel tests is we generate tests in that form, a random prefix to put the system into a random state, and then some parallel processes. And to decide if a test passed, then we see, can we find an order that explains the results that we see? And if we can't, then something went wrong. What went wrong is that at least one of the operations did not behave atomically. So what I'm testing here is atomicity of the API. That's only one kind of testing of concurrent systems, but very many operations are intended to behave atomically, and so this is actually a very generally useful kind of testing. Okay, yes. Here is the code that we write for running parallel tests. It's the quick check property. It's almost exactly the same as the one for sequential tests. All we do is we say, generate a parallel test case and run a parallel test case. Most of the code in our specifications is not the property. It's the state machine model, the state transition functions, the post conditions. Those are 100% unchanged in order to run parallel tests. And that, I think, is something very, very attractive about this approach. It means that once you've developed sequential tests, it's the work of moments to test for race conditions. Okay, I actually have the dispenser here. Let's see if it works. First of all, I have 2 properties. I have a sequential property. Let me test that first. So that tests that my model corresponds to the implementation. Okay, if my model is wrong, or if there's a bug that appears sequentially, then there's no point running parallel tests. It's much better to find it with sequential ones. Now I know that my sequential model corresponds to the code, so let me run the parallel tests. Whoa, they failed. We shrunk the failing test case. Here is the minimal counterexample. First of all, in the prefix, you don't have to do anything. Then you call take ticket twice in parallel. Sometimes they both return 1. And QuickCheck says, no possible interleaving. We found a bug. There's the code that I wrote for take ticket. I implemented a global variable in Erlang. I read it, and then I wrote back n+1. It's a critical section with no protection. Of course it doesn't work. But what I wanted to show you was that QuickCheck finds that race condition very fast indeed. OK, that's the ridiculous. Back to the sublime. What does debts actually do? It's a tuple store. It just stores Erlang data, and the first component of each tuple is considered to be a key. So then there's a bunch of operations, and they're quite simple. You can insert a list of tuples into a table. You can delete all the tuples with a given key from the table. You can insert new, a list of tuples. What's insert new? Well, it's like insert, except that if any of the keys is already present, then it's a no-op. And it's also atomic. So it's an atomic way to test and see whether a number of keys are in the table. And there are some more. They're straightforward. It's very easy to model this with a simple, purely functional program. I can almost just use a list of tuples to represent what I think should be in the table. And then modeling insert, you just append the new tuples to the ones you've already got. Modeling delete, you can write a list comprehension that just removes the ones with that key. So the specification, the model, is very, very simple. In fact, it's less than 100 lines of code to specify the key parts of debts. The implementation, meanwhile, is in 4 modules, and it's more than 6,000 lines of code. Why? It's building hash tables on the disk, and there's all kinds of complicated stuff going on in there. But its behavior can be specified very simply. OK, so I took debts, I wrote my simple model, I added the property that said test for race conditions, and within a few seconds, I found the first bug. I want to show you the bugs I found. In this one, in the prefix, we open the file. That makes sense, of course. And then in parallel, we do 2 things. We do an insert, and look, I'm inserting, and let's see, am I able to write on my slides yet? Yes. I'm inserting an empty list of tuples. It's a no-op. And in parallel, I'm doing an insert new of an empty list of tuples. That's also a no-op. They both returned OK, and yet QuickCheck says, no possible interleaving. Why is that? Sometimes you just have to read the documentation. That's the documentation of insert new. Notice the result type? Even in Erlang, OK is not a Boolean. A Boolean is true or false. So this function is insert new is supposed to return true or false, and in sequential tests, it always does. But when you run a parallel one, it returns OK. Where did that come from? Here's the second one. This one, in the prefix, you open the file again, and then in parallel, again, we do an insert and an insert new, but this time, I'm inserting a tuple in each case. You can also just give a single tuple. So I'm inserting 0, 0 here, and I'm inserting 0, 0 there. And what happened was that the test timed out. And I thought, oh, what's going on? This is a bit strange. But at the same time, this message appeared. Debts, bug was found when accessing table. So I thought, oh, that's probably a bug then. Here's a third failure. So this one is nice. In the prefix, we open the file, and then in parallel, we do 2 things. We open the file again. You might think that's odd, but it's not. This is designed for use in Erlang, where many processes may be using the table at the same time. And of course, each process that uses the table is going to open it. probably. So it's definitely allowed to open the file many times in parallel. So in parallel with that second open, we insert a tuple into the table, and then this get contents, it's an operation I wrote, that extracts the entire contents of the table, and it contains nothing. So I actually saw this bug in a number of forms. Basically, if another process is opening the table at the time, then your process may see a sequentially inconsistent view of the state of the table. That's not nice. So I sent these bug reports off to the guy who maintains debts, and he fixed the bugs and sent them back to me and said, oh, thank you very much. It's nice to find those. But I don't think they're the bugs that have been appearing at Klarna, because the symptoms are different. So I thought, well, that's a shame, and I began to run lots more tests, and well, they were passing. So we added one more statement to the property. We knew that file corruption was involved. So I added a final condition to my property that said, after running the tests, the results are okay, and the file is not corrupt. And I could write a very simple, one-line test that would see whether corruption had occurred. I did that, I ran a few thousand tests, and this appeared. So in the prefix, you open the file, you close it again, you open it again, and then you do three things in parallel. You look up the key 0 in the table. Well, it's not there, that's all right. You insert 0, 0, and you insert 0, 0 again. So 2 insertions and 1 lookup. And the result is okay. All of these return values are consistent with the spec. But when we checked for corruption, I got a premature end of file. Now I want to emphasize that this is a minimal counterexample. I saw this and I thought, open, close, open. That makes no sense. Surely it must fail if I just open the file once. I ran tens of thousands of tests, perhaps hundreds of thousands. They all passed. You really, really do have to open, close, and open. I know why now. It's because we start the test with the file non-existent. The first open creates the file, then we close it. The second open reopens an existing file. It's slightly different. We end up in a slightly different state, and that difference is critical to this bug. Also, you really need to do 3 things in parallel in order to provoke this. With only 2 processes, you never see it. So that was very nice, and premature end of file was one of the symptoms that had been reported from Klarna. So I was pleased with myself. And then I was giving a talk at a developer conference in Denmark, and sitting in my hotel room, I was supposed to talk about something else, but I thought, this is such a great story, I must tell it. But I hadn't saved the output from QuickCheck, so I had to rerun my tests in order to get something to put on my slides. And as I did that, this happened. Okay, so in the prefix, we opened the file. Now we actually insert something into it, the tuple 1, 0. And then in parallel, we reopen the file in the second process. And in the first, then we look up something that's not there and delete the thing that is. Once again, all the return values are consistent with the specification. But when we checked for corruption, we got bad object. So that was cool. Here's what Tubbe had written in the mailing list. We've got bad object and premature end of file every other month for last year. So it looked as though these 2 bugs could be the cause of the problems that have been hurting Klarna so much. Interestingly, I sent these bugs to the developer. Every time he got the failing test one day, he sent me back the fixed code the next. So what that shows is how much easier it is to find a bug when you have a small example than when you just have a failure in production. In fact, before I did this work, then a lot of work went into trying to find these bugs at Klarna. I know that Hasse Belinder, the developer of the code, spent more than 6 weeks at Klarna trying to track these things down. And they didn't find them, but their conclusion was, it seems to happen when the database is about a gigabyte. Maybe it's something to do with rehashing. So in reality, we could provoke the faults with a database with at most one record, and we needed only 5 or 6 calls to reproduce them. And every bug took less than 1 day to fix, given those minimal counterexamples. And I think this shows really how hopeless it is to try and debug a race condition from an error report in production. Because so much irrelevant nonsense has happened by the time you hit it, that figuring out what the fundamental cause was, is just impossibly difficult. Okay, so property-based testing, I've shown you it's easy to apply it to functional programs. We can apply it to imperative programs. We can apply it to concurrent programs. And we found bugs in everything we've ever tested. So there are a lot of bugs out there, and testing against properties is an effective way to find many of them. It can actually be cheaper than conventional test automation. I showed you the difference in size between our test code for FlexRay and a handwritten test suite. That difference in size translates into a big difference in cost. But even so, we're using formal specifications. A quick check specification is a formal specification, but we don't have to do any proofs. And that's great, because proofs are expensive. So we found a very cheap way to make use of formal specifications and to try out using them to improve the quality of all kinds of real industrial software. And the hardest part, it turns out, in applying quick check is coming up with those formal specifications in the first place. That is the constant challenge, both coming up with them ourselves and transferring that ability to Cubic's customers. It's a lot harder than you might think. I'm done.
How do you minimize the failure?
Oh, so the basic idea is that we have a test case that failed, and then we just create a smaller test case and rerun the test. We keep doing that, and if we find a smaller test that fails, then we use that as the starting point for further minimization. So it's a kind of greedy search until we find a test case where all of the strategies we have for finding the smaller case produce a test that passes. Then the search stops. And exactly how we do the minimization, it's really domain dependent. I mean, there are a lot of strategies built into QuickCheck, but also sometimes it's only the specifier who can think of an interesting way to simplify a test. For example, at one point, we were getting very long minimal test cases from instant messaging server. And in the end, we realized that the reason they were so long was we were testing a property with a timeout. And so the tests couldn't shrink. We should shorten them about 30 commands, because the test had to keep going long enough for the timeout to happen. So what we did then was we introduced a sleep operation in the tests, and we said, you can shrink any command to sleep, and bingo, we had 4 or 5 commands in test with sleep exactly where you have to make the timeout to occur. But QuickCheck can't know in advance that that shrinking step is useful in this application. So, when you're debugging something manually, you think about, well, how might I simplify this test to get something that's easier to understand? So you can still use that creativity, but now you come up with not a shrinking step in one case, but a shrinking strategy of your own that you can apply in every time you test that.
Have you heard of a tool called Coverity?
Sure.
Yeah. So they do something like, at least as part of the paper, it's like inferring policies from the source code. Have you looked at anything like that?
So Coverity, they're a static analysis tool. And we are not doing static analysis. And we're also starting from a specification. So there's another, where it's tested random testing branded in Microsoft Research. But one difference between QuickCheck and these tools is that many other tools try to do some automatic analysis, where you take the code, you don't require the program to tell you what it's supposed to do, but you still try and find errors. And you can find lots of errors that way. The difference in what we're doing is that we really do require a specification, and we're testing the code against the specification. So I think they're probably complementary approaches.
So with Microsoft research that told me that the PRM testing is really ineffective because of the way the space possible inputs and often bug refining inputs are very rare. And so they put a lot of work into combining that with feedback and that analysis to produce interesting test cases. What's your take on this?
So are you talking about the feedback-directed random testing? Randomly? Yeah, so I think they need, if you read the evaluations that they do, they say, well, random tests usually fail very, very quickly. And that means that we're unlikely to get deep into the code that we're testing. It's only kind of surface kind of testing. And so they use feedback to note that, well, here's a test that actually managed to run the 3 steps, and it created some values. Let's see if we can extend this test case further, and thus build up longer, interesting tests. So we don't use that approach, but certainly if we write by hand generators for our test cases. You saw actually one of those generators that said include, put, get, and what was the size in the test of my C code. So when we write those generators, if we completely ignore the semantics in the code that we're testing, then sure enough we get tests that fail very quickly. Then we start refining the specification. We add preconditions that prevent the test doing stupid things. We maybe adjust the distribution of test data so that we are more likely to generate longer, interesting tests. So we can generate very long and interesting tests that get very deep into the code that we're testing. But it's a process that's done by the specifier as part of understanding the specification of the code. Does that answer the question?
You said that proofs were expensive while testing is more cheap. I wonder if there is some work on combining proofs in the specification that would be like true, and the testing would be like conjecture on your model.
So I think
you have evidence that they work, but you don't have the proof, but you're confident that.
So certainly, if you want to prove things about your code, I think it's a very good idea to test those properties first. And then, you can at least avoid wasting a lot of effort on trying to prove things that aren't true. What I was saying about cost of proofs, well, Xavier was talking about the cost of developing a construct. And it was roughly an order of magnitude more costly to do the proofs than to write the code. If you look at testing, you'll see various figures for the cost of testing, but roughly 50% of cost of development is usually taken to be testing. And you said, Xavier, that you were talking about time to write the compiler without testing it. But I don't believe that you would mean the time to write the compiler. Just write the code, make the type check, and then put it in the version control. Of course, you run it and do some testing during that development, but not the final system testing, which would normally be quite an expensive process. But I think, from this kind of experience, it seems that proving complete functional correctness is maybe 5 to 10 times more expensive than establishing functional correctness well enough by testing.
But do you see some possibility of some new framework that can combine proofs that are cheap with testing where it is more appropriate? That's combining, merging somehow the mechanisms for more.
So things like Isabelle have a version of Quick built in nowadays, so that you can test as part of the process of developing proofs. And I believe that works nicely. And also, of course, there are all kinds of approaches that prove not full correctness, but simple properties that can be proven completely automatically. And so there's lots of work obviously on making proving things cheaper and more applicable. At the same time, there's also lots of work on making testing both cheaper and more effective. So I think I don't think there's a black and white situation. So both techniques will be useful in the future.
I think this is really cool. I'm a little curious about your quantifier elimination. Is it purely outside in random testing, or do you do a dependency analysis like ACL2S does?
No, it's purely, the pearls, they're purely random generation outside in. Then they have an interaction with shrinking, which is much more complicated. But at the moment, we generally speaking, they're quite simple to observe.
How do you deal with the problem of bias distribution, where distribution is not covering the space that you actually want?
We measure statistics on the test cases. So, for example, if I'm generating tests or a sequence of calls, I'll measure the length. I'll measure the percentage of each kind of call in the tests. If I see there's one that doesn't arise often, perhaps it's because I don't get into a state that meets a precondition often enough. I'll look at, I'm not a big believer in code coverage measurements. People have far too much faith in it. But nevertheless, it can be useful to look at coverage and see, well, here's a big part of the code that we're not testing at all. That's a warning sign, and a sign that we need to modify the distribution. So, in talks like this, I don't go through that process, but certainly when you apply these kind of techniques for real, it's very important to look at the distribution of data, the distribution of tests, distribution of execution of different